Good morning, everyone. I am Marcos Casanova Paez, postdoc in Professor Nice's group here in the Max Planck Institute. In the last 2 years, I've been developing single reference methods for excited states, with a special emphasis in open shell systems. Today, I want to share with you our recent advances in this topic. So let's begin. So first, I will give you a small theoretical background of the correlation energy problem and how this is solved by using Capra cluster theory. Then I will move to excited states by using the equation of motion theory. But most importantly, I will explain how the not very well known similarity transform equation of motion is done in ORCA. I will comment on its accuracy in 2 different benchmark sets, and then I will conclude this talk with the new features available in ORCA, but also what will be the next steps we are going to take in the future for excited states for open shell systems. There are essentially 2 different types of correlation energies. The first one is called the static correlation, and this is the correlation energy of electrons that are far from each other. This happens, for example, when you study bond stretching or dissociation curves. And for this, normally you use multi-reference methods such as CASPT2 or NetPT2 and so on. The other type of correlation is dynamic correlation energy, and this is the correlation energy of electrons that are close to each other. For this, we normally use single reference methods such as Capra cluster theory or density functional theory and so on. So if we focus in the first one, in Capra cluster theory, the answer is actually quite simple. It just says or proposes that your correlated wave function is not only your Hartree-Fock solution, but it can also be in an excited state. So you basically create a linear combination that represents the ground state, in this case the Hartree-Fock, or different excited states, which are given by this T operator, which is known actually as the excitation operator. However, we can say a little bit more about this excitation operator's T. The excitation operator can be divided into classes, T1, T2, T3, and so on. T1 is known as the single excitation operator because it's going to excite one electron from the occupied orbitals to the virtual ones. You also have the double excitation T2 when you excite 2 electrons, or you can excite 3 electrons, and so on. The main idea is the more ingredients you include in this expansion, the more correlation energy you recover, but this comes at the expense of a also higher computational demand. It is possible to see these operators in diagrams. For example, here I have the T1 operator, and this is actually understood in the following way. You're going to excite one electron from the occupied orbital I, and you're going to put this electron into the virtual orbital A. You can repeat exactly the same, for example, with T2. In this time, you take 2 electrons I and J, and you're going to excite them into A and B. You can also use T3 when you excite 3 electrons, and so on. Now, depending on where you truncate the T operator is actually the method you're going to get. For example, if you truncate at T1, the method is going to be Capra cluster singles. If you truncate at T2, this is going to be Capra cluster single doubles, or CCSD. At T3, Capra cluster single doubles triplets, or just CCSDT. And you can see down the computational cost. The first one is n to the power of 4, n to the power of 6, and 8, where n is the size of your system. In equation of motion Capra cluster, we have to consider 2 Schrödinger equations. One of them is going to be your ground state Schrödinger equation, which is going to be the Hartree-Fock, but also one for some excited state. Now you can combine these 2 Schrödinger equations and you come out with a different equation, which is given by the last term over here. So the new operator R is essentially and also another excitation operator, but this time you're not gonna do these excitations into your Hartree-Fock, but you're gonna do it into your Kaplan cluster wave function, which is the one that includes also correlation energy. Just like in ground state, these R operators can also be seen as diagrams. For example, if you are doing excitation energy equation of motion, or simply called EOM-CCSD, the operators R1 and R2 look like this. You excite one electron I into A, or you excite two electrons I and J into A and B. And you can see also the computational cost. The only difference with the previous one is that now this is an iterative, because you have to repeat this for each one of your roots. You can also study different kind of excitations, for example, ionization potentials. And the only thing you have to do is to modify how your excitation operation looks like. For example, the R1 now, it's gonna take one electron from the occupied orbital I, but this time you're not gonna put this electron into the virtual orbitals, but you're actually gonna remove it from your system. And that's why you're gonna have the other line A here. And also you can include double excitations when, for example, you excite one electron J into B, but the electron I is going to be removed from your system. In a similar way, you can also study electron affinities. So in this case now, you want to bring an electron from the affinity into your system. So if you see the R1 operator now, there is no electron I coming here, but actually you're bringing the electron from the infinity and you're going to put it into the virtual orbital A. In the same way, if you see R2 now, you excite one electron from J into B, but the other electron comes from infinity and goes into A. And finally, the similarity transform equation of motion. The sentence here is actually a summary of the whole idea behind this method. And it says you have to apply a second transformation to your Hamiltonian H, and then you have to diagonalize this resulting transfer Hamiltonian G only over single excited states. I know it sounds very confusing, and actually the first time I saw this, I was pretty much like this. Like, what actually does it mean this? But the idea is actually pretty simple. Let me explain it. So on the left-hand side, we have the equation of motion CCSD. So in this case, we take two electrons I and J, and we are going to put them into A and B. So the similarity transform equation of motion says that we can replace this problem by using a combination of, for example, the IP equation of motion CCSD and a single excitation. And the way to do this is by just simple putting these two diagrams together. And now you can see that I have the same structure on both sides. In both sides, I have two electrons I and J that are going to be excited into A and B. And you can repeat the same idea, but now using the electron attachment. So if we do exactly the same and we put them together, you can see that you have the same on both sides again. However, the similarity transform equation of motion still has another possible combination, which is actually the key of the success of this method. And this is by using the IP equation of motion, the EA equation of motion, and the single excitation all at the same time. If you put them all together, you will see that actually this resembles a triple excitation, and this is actually known as the implicit triplet excitation. It also has another advantage, because when you apply the IP equation of motion followed by a EA equation of motion, this is actually the definition of a charge transfer excitation. And this is a very well-known problem in equation of motion CCSD. Now let me show you about the accuracy of the similarity transform equation of motion. In this case, I have a small organic radicals benchmark set that contains 23 molecular radicals and 51 transitions. The reference for this is called CC3, And this is another Kapper cluster method. It's actually known as the approximate Kapper cluster CCSDT. And this is an approximation to equation of motion CCSDT. The scaling of this method, however, you can see that scales as n to the power of 7. So the question is, how does the similarity transform equation of motion perform when we compare it to the normal equation of motion CCSD? And the answer is this one. As you can see by the statistics, both methods actually yield the same accuracy. And you can see this by the mean absolute deviations, but also by the root mean square deviations. However, the similarity transform equation of motion has an advantage because it has a lower mean deviation. And this means that actually this method predicts the excitation energies in a balanced way. Another benchmark set now includes transition metals. In this case, we have 11 diatomic molecules that has singlet and triplet excited states and also doublet excited states. In this case, I will only focus on those ones with open shell systems, which are the last four highlighted here. This then constitutes 16 double excitations, and the references are CC3, but also equation of motion CCSDT. As I mentioned previously, CC3 is actually an approximation to EOM CCSDT, and therefore we're going to use this one as the reference. However, pay attention to the scaling of this method as it goes as n to the power of 8. So now the question is, how does the similarity transform performs compared to not EOM CCSD, but to CC3? And you can see the results here. So essentially, the similarity transform actually has an excellent agreement and has the same performance as CC3. And you can see this by looking into the mean absolute deviation and also the root mean square deviation. Both methods, however, seems to underestimate a little bit the excitation energy with a mean deviation that is almost zero anyways. And finally, the new features that will be available in ORCA 6. One of these changes is the complete reimplementation of the OpenShell equation of motion code into the ORCA MDCI module. And this includes the IP equation of motion CCSD, the electron attachment equation of motion CCSD, and also the similarity transform equation of motion CCSD. And it's because of this reimplementation that we have seen speed ups of 3 times when we compare it to the previous version of ORCA 5. So on the table on the right, you can see the timing for the similarity transform equation of motion and also the equation of motion CCSD in different versions of ORCA. And you can see that in ORCA 6, for a benzene dimer with a double setup basis set, it took about 47 minutes. On the other hand, when you use ORCA 5, it took 161 minutes. And something very similar happens when you compare it to the normal equation of motion CCSD, where the similarity transform equation of motion performed 3 times faster than both of them. As a second example, we also have the 1-benzene molecule, but this time with a larger basis set, but the results are still consistent. The similarity transform equation of motion in ORCA 6 is still performed between 2 and 3 times faster than the version from ORCA 5. Another feature that's going to be available in ORCA 6 is going to be the additional information about your excited states when you use the useSim symmetry keyword. In this case, you will be able to see the spin expectation value S squared and also the excited state symmetry. In this example, I showed the results for the benzene molecule. So you can see here that the root number 3 and number 4 correspond, both of them, to triplet excited states, and the root number 5 is going to be then a single excited state. And you can see also next to it what is going to be the symmetry of this excitation. And finally, what is going to be the feature of ORCA for single reference excitation energy for open shell systems. First, you can expect the core ionized and also the core excitations for open shell systems either in IP equation of motion CCSD and also by the similarity transfer equation of motion CCSD by using the core valence splitting. Here I show you an example for the OH radicals for IP equation of motion CCSD. On the top, when you remove an alpha electron or a spin up electron, and down when you remove a beta electron. And here you can see the result path for the similarity transfer equation of motion CCSD. And here you can see that the excitation energy by using this similarity transfer equation of motion CCSD is almost identical to the experimental energy as provided here in the reference. Also, you can expect soon the open shell versions or the del piano equation of motion methods. And this is going to include the del piano IP equation of motion CCSD, del piano EA equation of motion CCSD, and of course the del piano version of the similarity transform equation of motion CCSD. And finally, I want to thank Professor Frank Nisse for giving me the opportunity to work in this project here in the Max Planck Institute. I also want to thank Ute Weger, Dagmar Lenk, and also Axel Kozlowski, who helped me with the MPI parallelization, the debugging, and also the symmetry handling in ORCA. I also want to thank the Max Planck Institute for all the computational and also the financial resources, and of course to you, the ORCA users. Thank you so much.